I guess it's not quite an introduction. It's just a pleasure to have as today's speaker our very own Akhil Mathew, who will talk about Algebraic K-theory, traces, and arithmetic.
Okay, yeah. So thank you very much for the invitation and for having me. Yeah, so I guess I would like to talk about in general about the subject of trace methods in algebraic K-theory and the connection to and some of the connections to arithmetic or maybe to p-adic arithmetic, I should say. Okay, so right, so maybe let me start with introduction. So let me start with K0. So let R be a ring. So right, so I want to talk about higher algebraic K-theory. Let me start with K0. Sorry. Okay.
Maybe so people should mute themselves except if they have a question. Okay, thank you.
Thanks. Yeah. Okay, so right, so let R be a ring. Right, so then we define K0 of R to be the Grothendieck group of the category of finitely generated projective R modules. So in other words, right. So in other words, it has generators. So the generators of this group are coming from isomorphism classes of finitely generated projective modules. So the generators I'm going to denote as brackets P, if P is a finitely generated projective R module. And then there are relations. So brackets P direct sum, brackets P plus brackets Q is given by the class of it's given by the class of brackets. It's given by the class of the module P direct sum Q. Right. So this is defined by generators and relations. And so another way we can think about it is that we consider all finitely generated projective R modules up to isomorphism, and that's an abelian monoid, and we can form the group completion of that. So that universal way of having inverses to that. Right, so I guess it's been sort of known from the beginning that K0 is related to algebraic and arithmetic geometry. Right, so for example, K0 of a field is the integers, just taking the dimension of a finite dimensional vector space. Right, so if E is a number field, then K0 of the ring of integers in E is given by Z direct sum the class group, or the Picard group of OE. Okay, so this definition also generalizes to schemes. So let's say we have a quasi-projective scheme. So I'll say this mostly as an aside, but so a remark is that this definition, this definition generalizes to quasi-projective schemes. We have to modify it just a little bit. So if X is a quasi-projective scheme, then we can define K0 of X in sort of a similar fashion, but using vector bundles on X. And we have to impose, so the vector bundles are going to give the generators, and the relations are going to come from short exact sequences of vector bundles. So define K0 of X as, well, you do something similar, so you get a class for every vector bundle. And then you get the relation that brackets E is the sum of brackets E prime plus the sum of brackets E double prime if there's a short exact sequence. 0 to E prime to E to E double prime to 0. Yeah, so it's not only direct sums because the extensions don't have to split. Okay, right. So so K0 is related to algebraic and arithmetic geometry. So I mentioned that it recovers a class group. But another sort of important example of K0, at least rationally, comes from the case of a smooth quasi-projective variety over a field. So if X is a smooth quasi-projective variety over a field, little k, right, so then there's a canonical isomorphism. There is an iso of rings between K0 of X tensor Q and the Chow ring of X tensor Q. So the Chow ring of X is, right, so this is defined by considering algebraic cycles on X. So this is defined in terms of algebraic cycles on X modulo the relation of rational equivalence. And it's made into a ring by taking the intersection product of cycles. And so the statement is that this Chow ring, which is an object that actually, it takes some work to actually construct this, to define this formally and construct this as a ring, because, for example, if you want to intersect two cycles, cycles are given by subvarieties on X, and if you want to intersect them, you have to move them so that they are intersecting. They're intersecting in the right codimension, for example. So this term on the right hand side actually takes some work to define, and already this isomorphism. So this isomorphism comes from the turn character. This isomorphism is kind of saying something sort of interesting because K0 is something that you can define very easily. So in this isomorphism, so note that K0 is something that essentially you have for free. Once you have the notion of a vector bundle or a finitely generated projective module, you can just define K0. So K0 is something that exists for free. But if you look at the right-hand side, the Chow ring, that's actually something that requires some theory to construct. And so in particular, if you look at the right-hand side, this Chow ring, it's something that's defined for smooth quasi-projective varieties over a field, but it's not really something that makes sense if you have a singular variety, for example, or a variety or some sort of scheme in mixed characteristic. But note that K0 is something that's defined somehow extremely generally. So in fact, the right-hand side is not defined nearly as generally. So one sort of takeaway from this is that K0 gives a way of thinking about intersections that somehow, well, at least if you work with rational coefficients, K0 gives a way of thinking about intersections that work sort of very generally, that they don't require any sort of smoothness, and that you can build without really doing doing any hard work to think about algebraic cycles. Okay, and so in fact, this point of view has been useful. K0 has been used to solve sort of various intersection theoretic problems. For example, in cases where you don't actually have a Chow ring. Okay, so I think one of the ideas that came from the beginning in algebraic K-theory is that K0 is some sort of cohomology theory. It's supposed to be something like a cohomology theory for algebraic varieties. Or rather, it's supposed to be one sort of piece of a cohomology theory. So K0 is supposed to be part of some type of cohomology for algebraic varieties, for schemes. Right. I guess the motivation from this comes from algebraic topology. So in algebraic topology, there's also a version of K0. So if X is a finite CW complex, So then one defines what I'll write as ku upper 0 of x to be the Grothendieck group, also somehow defined similarly, of complex topological vector bundles. So I mean, you do the same construction, but for topological vector bundles instead of algebraic vector bundles. Right, and so I guess it was shown maybe in the 50s that this is sort of the 0th part of a cohomology theory, sort of a generalized cohomology theory on spaces. And here cohomology theory is in the sense of Eilenberg and Steenrod, so it satisfies sort of the familiar axioms of cohomology like homotopy invariance, excision, and so forth. But the value at a point is not just z in degree 0. So this defines a cohomology theory on spaces. So let's say on finite CW complexes for now. And this cohomology theory, so this was, I think, maybe the first example of a cohomology theory that's not singular cohomology. And this cohomology theory was already powerful enough at the time to solve sort of various topological and geometric problems. And I guess nowadays, this example of topological K-theory is really sort of seen as one of the fundamental examples of a cohomology theory. And it's sort of extremely important in the homotopy theory. But okay, so I think algebraic K-theory and topological K-theory sort of developed. Well, they sort of both influenced each other in both directions. And the idea that topological K-theory gives a cohomology theory also sort of motivated the idea that algebraic K-theory should give something like a cohomology theory. So I think maybe this was one of the motivations for the search for higher algebraic K-theory. So suggests not only to look at K0, but also higher K groups. Right, and so okay, so maybe now we'll talk a little bit about higher K theory. So so this problem of defining sort of higher algebraic K groups, sort of in analogy with what happens in algebraic topology, that you can build this whole sort of cohomology theory. So I should say that this is, it's a Z-graded cohomology theory. So you can define KUI for I not 0. Okay, so there was the problem for a long time of defining higher algebraic K groups, say for a ring or for a scheme, and I guess developing their properties. And so this problem was solved by Quillen. So Quillen defines for a ring R higher K groups K, right? So groups Ki of R for I greater than or equal to 0. So higher algebraic K groups. Right, and so these higher algebraic K groups are the homotopy groups of a space or of a spectrum. So these are the homotopy groups of a space called a K-theory space. And well, somehow the idea is that well, K0 is defined in terms of isomorphism classes of finitely generated projective modules. And the idea is that you should, well, I guess the idea is this is some homotopy theory, so you should remember the automorphisms of finitely generated projective modules. Right, so in particular, you should see something like the classifying spaces of general linear groups of the ring R showing up. And this is in fact what happens. So the space is built from, sort of built in some manner from finitely generated projective R modules. And their isomorphisms. Right, and so Quillen sort of writes down or constructs a space whose higher homotopy groups are defined to be this K-theory space. So right, so maybe I should say that these higher K groups are in general very difficult to compute. These are very difficult to compute in general. So there are actually very few examples where higher algebraic K-theory is completely computed. So there are not so many rings for which one knows all the K groups, and maybe the most famous example is the case of a finite field, which Quillen computed. So very early in the subject, Quillen computed the higher algebraic K groups of a finite field, but there are somehow very few sort of complete computations. So for example, the integers is not known. And right, so I guess it's very difficult to compute higher algebraic K-theory in general because, well, it's the homotopy groups of some space, while higher homotopy groups are in general much more difficult to access, and also the space is somehow very difficult to access because it involves these big general linear groups of the ring R. Right. So okay. So how does one sort of access and describe higher algebraic K-theory? So one of the most powerful tools in the subject that I think has influenced a great deal of research around higher algebraic K-theory and algebraic cycles and so forth is the Motivic spectral sequence. So maybe I'll continue. So one of the main tools which gives sort of a really strong description of higher algebraic K-theory, at least with the l-adic coefficients, is the Motivic spectral sequence. So one of the main structural tools, in describing higher algebraic K-theory, right? So it arises somehow in a very different fashion. It doesn't arise necessarily from sort of the definitions of K-theory, the immediate definitions of K-theory, but it arises from sort of various properties of K-theory and relations to sort of algebraic cycles. And so one of the main structural tools in the subject is the Motivic spectral sequence. I want to say a little bit about that. So, so the Motivic spectral sequence is a tool that is again sort of motivated by something in algebraic topology. So this is an analog of the etale-Herzberg spectral sequence in algebraic topology. For topological K-theory. And so let me just mention that, right, so the etale-Herzberg spectral sequence. So in general, when one has one of these sort of cohomology theories in algebraic topology, then there's always a way of relating it to ordinary singular cohomology. So for example, if you want to compute the topological K-theory of a space, there's always a spectral sequence which starts from the cohomology, just a singular cohomology of the space, and converges to the topological K-theory. So this is a spectral sequence which goes from the singular cohomology of a space. Well, sorry, I shouldn't write the arrows in that way. So it's a spectral sequence which starts with the singular cohomology of a space and converges to the complex K-theory. So this is a basic tool in algebraic topology that makes sense for any cohomology theory. And the idea is that the Motivic spectral sequence is supposed to be an analog of that in algebraic K-theory. It's supposed to be of similar sort of great computational power. But maybe right. So maybe one difference is that I guess in algebraic topology, singular cohomology comes way before K-theory. But it's sort of the reverse historically in this setting. So K-theory came first, and then the analog of singular cohomology came a lot later. Okay, so let me say a little bit about this Motivic spectral sequence. So this is a construction. So it was conjectured by Beilinson and developed by Friedlander, Suslin, and Levine. So Friedlander, Suslin, and Levine, conjectured by Beilinson. Right. So let X be a smooth quasi-projective variety again. Over a field, over some base field K. So then there's a spectral sequence Right, so it goes from the Motivic cohomology of X with weight J converges to the Algebraic K-theory and degree 2J minus I of X. So at least formally, it's supposed to look, it's sort of indexed by like the classical equivalence for a spectral sequence. So the output is given by the K groups, by the higher K groups, and the input is given by these Motivic cohomology groups. So the so these Motivic cohomology groups, these groups HI mot of X with Z of J coefficients. So these are equivalently the higher Chow groups of X, which were defined by Bloch. These are defined by Bloch, and these are some sort of these are defined in terms of explicit complexes involving algebraic cycles. So these are defined by Bloch via considering algebraic cycles on X cross some affine space. So in particular, these Motivic cohomology groups, they generalize the Chow ring. So in so in H2J of X note with coefficients of Z of J is exactly the Jth Chow group of X. And in fact, what happens is that the spectral sequence is really a generalization. It's sort of a vast generalization of the isomorphism that I wrote down earlier between the rational K0 and the Chow ring. So the above spectral sequence, so it turns out the spectral sequence generates rationally. So the above is somehow a generalization. The isomorphism between K0 of X tensor Q and the Chow ring of X tensor Q. Okay. Okay. So the idea is that these Motivic cohomology groups, so these come from, again, so these are defined via some explicit complex of algebraic cycles. That this is supposed to be some sort of replacement for singular cohomology in the setup, and these are sort of the building blocks for the K theory, for the higher K theory. And in particular, these Motivic cohomology groups are some sort of generalization of Chow groups. And in fact, the spectral sequence is really sort of a vast generalization of the isomorphism between K0 tensor Q and the Chow ring. Right. Okay. So right. So this is giving a lot of information. I mean, the Z of J's are rather large complexes in general, but when one works with, but another sort of crucial ingredient in K theory is that these complexes of algebraic cycles can be identified in a completely different way with mod L coefficients. So this is right. So this is a theorem of Wygotsky and Rost, and it's the Beilinson-Lichtenbaum / Bloch-Kato conjectures. So this theorem states that these Z of J, so they're supposed to look kind of like Tate-twists, and in fact they sort of are the Tate-twists. So the statement is that if L is a prime number, which is not the characteristic of K, then okay, so this Z mod L twisted by J. So here I guess here you have to consider it as a Zariski sheaf or as a complex of Zariski sheaves. And then the statement is that it's the truncation in degrees at most J in the Zariski topology of the etale sheaf. The usual etale mu L tensor J. Right. So in particular, there's a usual sort of etale sheaf and somehow you're truncating it in the Zariski topology, which is a somewhat, it's a slightly difficult construction to sort of get an explicit handle on in practice. Right, so there's this. So in particular, that can lead to these Motivic cohomology groups being quite large. But yeah, so that there is this sort of explicit formula for them. Okay, sorry. So maybe I should just sort of concretely explain a couple of examples of this result and sort of what it implies. I mean, so this result. So I guess these two results really give a tremendous amount of information about the mod L K-theory of, say, a smooth quasi-projective variety, because you have the spectral sequence, and then you can identify the terms pretty explicitly. Well, with this, I guess this risky truncation is not it can be difficult to calculate in practice, but yeah. So maybe let me give the example. So suppose x over the complex numbers is an algebraic variety. Right, so maybe I should say it's smooth and quasi-projective. Right, and so then what can happen is that if you take K0 with mod L coefficients, it can be quite large. I mean, it can be some sort of infinite group. But what happens is that if you take the higher K groups, Ki of x, with the mod L coefficients, these will agree for I greater than or equal for I sufficiently large with the topological K-theory of the complex points. So with the mod L topological K-theory of the complex points. So I think it's kind of amazing. It's in general, algebraic K-theory is defined. It's defined in terms of algebraic vector bundles, and in degree 0 is related to the tau ring, which is this very sensitive invariant of x. But somehow in high enough degrees, it's a purely topological invariant. It only depends on the underlying homotopy type, and that's a consequence of this result. Right. Okay. So yeah. So this gives so these results give a great deal of information for the mod L K-theory of well, especially smooth schemes, characteristic not L. But there's some sort of questions, some motivating questions that one can ask here. So one sort of motivating question is that so the Motivic spectral sequence, well, the Motivic spectral sequence is something that makes sense integrally, and mod L one has this identification. And the question that one can ask is that do these constructions work if you're outside the case of smooth schemes over a field? So sort of maybe a motivating question for who I'm going to describe next in the talk is right. So this gives a lot of information about the K-theory of smooth schemes, but how does one study the K-theory of singular schemes? Or how does one study the K-theory of objects in mixed characteristic that don't live over a field? So how does one study the K-theory of singular rings or schemes or rings in mixed characteristic, ZP? So there are some reasons that the case of smooth schemes over a field, so there are many tools that make sense for smooth schemes over a field that somehow don't make sense more generally. And so, for example, something that I think is not really clear is whether there's an analog of the Motivic spectral sequence, or to what extent there is an analog of the Motivic spectral sequence. So to what extent is there an analog of the Motivic spectral sequence? Right, and so maybe just one sort of general comment is that a reason that this is more difficult, or a reason that this, well, at least it involves a different set of tools, maybe I should say, is that one sort of key feature of smooth schemes and one sort of key feature of K-theory is that it's A1 invariant. So if you add a polynomial generator, right, so remark is that if R is regular, then the K-theory of R is the same as the K-theory of R brackets X. So it's called A1 invariant. And somehow A1 invariance is really built in, or a lot of the tools that I'm describing, somehow A1 invariance is really really essential in the setup. So for example, it's really essential in the setup by Brodsky. The whole framework is built around A1 invariance. But this is really well, but this is false if R is singular. So not true if R is singular. Right. So just to give like a very concrete example, if one is interested in something like K-theory or well anything, any construction, one can try to ask about, say, its tangent space. One can ask about how it deforms. So one can ask, an example of such a question that one could ask is, one can ask about sort of infinitesimal deformations of K-theory. So something like the K-theory of the dual numbers, K brackets epsilon. And these types of questions are sort of not treated by the above techniques. Okay. So there's a different set of tools that that appears in studying these types of that arose originally from studying K-theory in these types of settings. That has also led to a lot of mathematics, and so this is sort of the subject of trace methods. So I want to say something about that. So the theory of trace methods is sort of an essential tool for answering these types of questions, and has also led to sort of advances in other areas of mathematics. Okay. Trace methods. Okay, so the starting point of the theory of trace methods is another type of construction that one can do for a ring that at least a priori looks very different. And this is called the Hochschild homology. So the trace methods are roughly methods that are tools that start with this are based around this definition called Hochschild homology. And so Hochschild homology is the following definition. So let R be an algebra over a base ring K, and I'm going to assume R is commutative for simplicity. So one defines the Hochschild complex HH R over K to be so it's the derived tensor product of R with itself over the derived tensor product of R with itself over K. So first tensor R with itself over the base K, and then consider R as a module over that, and tensor R with itself. So it's this tensor product. Right. So so one can describe this. So this is one sort of possible definition. So this is going to live, say, and consider this as a chain complex of K vector spaces. And so this can be described. Another way of describing it without using derived tensor products is, so this can be described via an explicit chain complex, or an explicit simplicial abelian group, an explicit chain complex, basically in terms of the various tensor powers of R over K. Right. And so maybe a priori this is looks a little ad hoc, but in fact this turns out to be a very sort of central construction. So this turns out to be a really fundamental construction for at least two reasons. And one reason is that, right, so a priori it's something that is defined in terms of the ring. But it turns out you don't actually need the ring to define Hochschild homology. You just need the category, again, of finitely generated projective R modules. So can be defined in terms of finitely generated projective. So it can be defined in terms of the category of finitely generated projective modules. So in the same way that K-theory is something that you define from vector bundles or finitely generated projective modules of a ring, Similarly, Hochschild homology is something that has this property. Classically, so that Hochschild homology is Morita invariant. So, right. So at least one other reason that Hochschild homology, Hochschild complex is somehow fundamental is that it's very computable, because basically it's some Tor groups, and all of this comes from maybe one of the sort of first theorems in the subject, which is the Hochschild Kuston-Rosenberg Theorem, which describes that if R is smooth over K, then the Hochschild homology groups are something very explicit. They're given by the algebra of differential forms, the algebra of algebraic differential forms of R over K. So this is Hochschild Kuston-Rosenberg. Okay. So right. So in particular, that means that even for singular rings, it ends up being very very computable in practice. Right. And so I guess the insight is that K-theory and Hochschild homology are related. So essentially, for I guess nowadays one can express it in terms of essentially sort of formal reasons, starting with item number 1 above. And so one can construct a map from the K-theory of R to the Hochschild complex of R over K, and this is called the Dennis trace. And so this turns out to be sort of a useful tool, for example, for detecting K-theory classes, because if you want to detect that some K-theory class, say, is non-zero, well, you can map it to the Hochschild homology, and the Hochschild homology is somehow much more computable, so it gives it sort of a tool for detecting classes. But in general, it turns out, right, so in general, Hochschild homology is sort of not, Hochschild homology over K turns out not to be a powerful enough invariant. So there are some limitations to this invariant, especially when one is interested in sort of torsion phenomena. So right, so here's sort of an observation. So this is right. So this is a map that one can construct for any base ring R. But sort of an observation that one makes is that so Hochschild homology depends on the ring R and it depends on the base K. But the algebraic K-theory doesn't depend on the base; it just depends on the ring R. So in particular, you can vary the base K, and in theory, you might get more information that way. So an observation is that in fact, you can always take K to be, for example, the integers. So it factors. So if you take the Dennis trace, it factors. So it goes into the Hochschild complex of R over K, but in fact, it factors over the Hochschild complex of R over the integers. So you're allowed to vary the base K, and in principle, if you make K sort of as small as possible, you might get more information. So in particular, you can take K to be the integers, Z. And so you might be able to, for example, detect more classes that way, because any class that you can detect in Hochschild homology over K, you can detect in Hochschild homology over Z. So, so taking K equals Z can give more information. Right, but it was still somehow realized that right. So this gives an improvement, but it was still somehow realized that that especially when one is interested in the torsion information, there's still that this is still somehow not optimal for the torsion information. So this is already sort of enough. Well, this and sort of taking into account symmetries of Hochschild homology, sort of enough if you're in characteristic 0. But it was observed that in for p-adic information, somehow this Hochschild homology over Z is also somehow not quite optimal. And the insight was that one should sort of build in one should use some more stable homotopy theory. So the idea was that to get an even more so it's observed that this tool of if you make the base ring K for Hochschild homology as the integers, you can get more information. But there's still some information that was missing. And the idea was that one should sort of enlarge the world that one is working with from the category of rings to the category of ring spectra. So one should develop the theory of Hochschild homology and K-theory, not only in the world of rings, but in this larger world of higher algebra and ring spectra. Right, and in this world, so the integers is the initial object in the category of rings, but that's not true in the world of ring spectra. In the world of ring spectra, you have the sphere spectrum, which is the initial object in the category of rings. So the idea was that one should develop the theory of Hochschild homology and K-theory. Right, I'll just say Hochschild homology in the world of spectra. And in this world where you're allowed sort of more exotic, more homotopy-ish rings, and in that world, the initial object in the category of ring, the initial ring is no longer the integers, but the sphere spectrum. So in higher algebra, the initial ring, put ring in quotes, is the sphere spectrum. And so the vision was that somehow you should do Hochschild homology over the sphere spectrum. So so the definition is that topological Hochschild homology THH of a ring is the Hochschild homology of the ring, but now where the base is not the integers, but the sphere spectrum. And so, of course, it requires some work to somehow make sense of this. But in the end, I guess Hochschild homology is sort of a very general sort of construction. I mean, it basically involves taking sort of iterated tensor products and taking a colimit, and so one can do that in this world of higher algebra, and one obtains this notion of topological Hochschild homology. And it turns out this is a very good thing to do, and this actually sort of sees a lot of information that you don't see by if you stay sort of in the world of classical rings. And so, for example, so here's sort of a basic reason that topological Hochschild homology turns out to be sort of a better theory than Hochschild homology over the integers. And so this is a point that Lars Hesselholt likes to make. And so this is maybe the first example of topological Hochschild homology, which is that if you take the topological Hochschild homology of FP, then what you obtain is very nice. It's this polynomial ring on a class in degree 2. But by contrast, if you consider the Hochschild homology of FP over the integers, then what you obtain is somewhat less nice. It's a divided power ring. It's a divided power algebra on the same class. So topological Hochschild homology maps to the Hochschild homology, and somehow what's a little bit surprising and miraculous is that when you consider topological Hochschild homology, these divided powers get replaced by a polynomial algebra. And this actually turns out to be, well, this was somehow the first example, but it turns out to be sort of the fundamental example that is used in all the sort of the developments. Okay, so yeah.
Akhil, can you just remind me what a divided power algebra is?
Sorry. So this means that right. So in general, the divided power algebra over Z would mean that you take Z brackets an element sigma, and then you add all the I powers divided by I factorial. And then you reduce it modulo P. So this is a divided power algebra over the integers. Right. Sorry, so maybe I should say that in a little bit more detail. Thanks. Right. So the divided power algebra over Z of a class X is a ring Z brackets X, and you add all the divided powers X to the I over I factorial. And this is a divided power algebra over FP, which means that you also mod out P. And so in particular, X is going to be the element sigma has its P power 0, because sigma to the P is divisible by P. So it ends up being this big tensor product of truncated polynomial rings. And so in particular, it's not such a nice ring for that reason. Yeah, thanks for the question. Okay. Right, so this is sort of one reason THH is a good theory, but another reason is that it actually turns out to have a lot more structure and a lot more symmetry. And this is really one of maybe this really sort of subtle and parts of the theory, which is still being studied and understood and being reinterpreted. So what I can just say is that, right, since I'm a little on time, so another reason that THH is sort of really powerful is that THH has extra structure. This is called this extra structure, not visible on Hochschild homology, not visible or not existent, I should say. Right, and so this extra structure is somehow right. So maybe one reason that a lot of this theory was developed 20 years after the development of K-theory, there's sort of more homotopical input that goes into this theory. But one has this extra structure, and then this leads to the definition of the theory of topological cyclic homology. So it leads to this extra structure called the cyclotomic structure, leads to another construction, a construction TC of a ring R called topological cyclic homology. So this is built from taking into account THH, but also taking into account this extra structure. And this extra structure, let me just remark, it's really essential for this extra structure to work over the sphere spectrum. So this is also a case where this extra structure is actually not there if you consider Hochschild homology over the integers or over any classical ring. But it's sort of essential to work in this world of spectra, higher algebra. So right, okay. So it leads to a construction. So right, so to make a long story short, it leads to a construction called topological cyclic homology, and sort of a refinement of the Dennis trace called a cyclotomic trace, which is now a map from K of R to TC of R. And so TC of R maps to THH of R, and this maps to the Hochschild homology of R. And this is called the cyclotomic trace. Right, so I should say this was initially constructed by Bockstedt, Shen, and Metzen in '93. And so, right, so it turns out this map called the cyclotomic trace. So yeah, so I should just say a couple things is that, right, so TC is somehow more difficult to define than K-theory, but it's actually much easier, or it's easier to compute because it can be computed using sort of tools of cyclic homotopy theory. And in fact, the cyclotomic trace turns out to be a very useful tool for sort of detecting classes in K-theory. So the cyclotomic trace is, well, this sort of subjective trace methods gives sort of a really powerful tool of answering the types of questions that I raised earlier, and in particular because there's this theorem of Dundas, Goodwillie, and McCarthy that describes sort of what this sort of does for you. So the theorem of Dundas, Goodwillie, and McCarthy is that if R is a ring with a nilpotent ideal, so then there's a pullback square where you have the K-theory of R, TC of R, K-theory of R mod I, and TC of R mod I. So there's a pullback square, and in particular, this means that if you want to study questions like what is like the tangent space of K-theory, what is the K-theory of the dual numbers, then essentially you have to do a TC calculation. Right, and so this result, by the way, was initially proved by Goodwillie if R contains the rational numbers, and if R contains the rational numbers, you don't need a topological theory. One can The theorem is then formulated purely algebraically in terms of algebraic Hochschild homology and so forth. But to get the correct p-adic information, one has to use TC, as I think was conjectured by Goodwillie before the theorem was, right. So maybe I can also mention. So this is sort of a relative theorem. It's saying that sort of the change in K-theory along a nilpotent ideal is the same as the change in TC, and that lets you sort of bootstrap sort of computations in K-theory, computations in TC along nilpotent ideals and so forth. There's also sort of like sort of an existing sort of comparison theorem that says that K-theory and TC are quite close to each other if you have a p-adically complete ring. Right. So I guess let me state this theorem. So this is due to Geisser, Levine, Geisser, Hasselholt, and Clausen, myself, and Morrow. Right, and so it states the following. So if R is a p-adically complete ring, then one can describe the relationship between K-theory and TC in the following fashion. So one is that TC is the p-adic etale K-theory of R. So it's a universal approximation to p-adic K-theory that satisfies etale descent for p-adic rings. So it's sort of a universal way of imposing this this condition of etale descent. So maybe since I didn't define that, maybe I should state that sort of comparison, which is that if R satisfies mild finiteness assumptions, then the map from the p-adic K-theory of R to TC of R is an iso in large enough degrees. Right, so somehow that'll, I guess, how large will depend on the residue fields of R. And so maybe let me not state the precise formulation here since I'm a little low on time. But essentially, right, so I guess this result is also saying that there's sort of a close relationship between p-adic K-theory and p-adic TC when you're working with p-adic rings. So essentially the theme is that TC is a tool that lets you sort of in particular study the p-adic K-theory of p-adic rings. And it's sort of a close approximation, sort of both structurally and sort of computationally. And in general, there's sort of a significant literature of on using trace methods and using TC to actually study the p-adic K-theory of p-adic rings. So there's a large literature on using TC to make calculations in algebraic K-theory. So for example, you can solve this problem of like the K-theory of the dual numbers. And there are lots of other examples in the literature by many authors. Maybe one sort of particular highlight that I'd like to mention is the work by Hasselholt and Madsen. So they computed the p-adic K-theory of local fields. So finite extensions of QP. Right, and so in this case, there's an answer that one gets from the Motivic spectral sequence and from the Valence-Lichtenbaum conjecture that was not known at the time. But Hasselholt and Madsen gave a p-adic proof in this setting. So using TC, and in particular, what Hasselholt and Madsen do is they relate TC to structures such as the de Rham-Bit complex that show up in sort of p-adic arithmetic geometry. Okay. Sorry, so I have about 5 minutes. So in the remaining time, I want to say something about the connections to arithmetic, or some of the recent connections to p-adic arithmetic. So yeah, so recently, maybe in the past few years, it's sort of been shown that thinking about TC and sort of related invariance can be used to sort of develop, well, thinking about TC and related invariance actually sort of produces structures in p-adic arithmetic geometry, sort of new and exciting such structures. And in fact, these connections, I think they were originally discovered. Using the methods of topological Hochschild homology. But so let me start by sort of stating maybe one of the theorems. So this is a theorem, and so this will sort of fit into the theme of the talk. And this is a theorem of Bott, Morrow, and Schulze. So the theorem of Bott, Morrow, and Schulze is that there's an analog of the Motivic filtration on TC. So classically, TC was sort of studied using sort of more homotopy methods, especially methods of equivariant stable homotopy theory. So the work of Bott, Morrow, and Schulze shows that there's an analog of the Motivic spectral sequence for TC. So so for any p-adic ring, then there is a Motivic. Sorry, I guess it's not exactly clear what the analogy is with. But anyway, so there is a Motivic spectral sequence, which goes from the cohomology of a complex called the ZPJ of R, and converges to TC in degree 2j minus I of R with p-adic coefficients. So there's an analog of this Motivic spectral sequence from Motivic cohomology to algebraic K-theory, but for TC, and somehow one of the key points here is that it works completely generally. So note that this is valid for any p-complete ring. So they construct an analog of the Motivic spectral sequence for topological cyclic homology that's valid for any ring R with arbitrary singularities, and where these terms in the E2 term, well, there are also objects that they define. These ZPJ of R are objects that they define, and these objects can actually be, well, they can be defined sort of purely algebraically now in terms of prismatic cohomology. So these are sort of a filtered Frobenius eigenspace on prismatic cohomology. Defined by Bott and Schulze. So it is something that you can define purely algebraically, though, using sort of new p-adic cohomology theories. Right, so maybe I should also say that for in low weights, j less than or equal to p minus 2, these turn out to be equivalent to objects called symptomic cohomology considered by Fontaine-Messing and Kato. So but anyway, sorry. So maybe the point that I sort of want to make is that one has an analog of the Motivic spectral sequence, but the terms involved are somehow of a very different flavor. So previously in the Motivic spectral sequence, things had to do with algebraic cycles, but now they have to do somehow with these prismatic cohomology theories. What I think is sort of Right. So what's sort of remarkable about it is that it's defined in a very different fashion from the Motivic spectral sequence of K-theory. In particular, it's defined using a very different set of tools. And these ZP of J's in general are something that I think is kind of are objects that are of interest in p-adic arithmetic geometry, and they're known in some cases, but they're not necessarily known in others. And yeah, so I think, well, I'm out of time, but maybe I just want to sort of end with sort of the general point that something that I think is kind of remarkable is that thinking about topological Hochschild homology, and which maybe started with K-theory, and about its structure, actually leads one, or has led various authors to these sort of very deep and new sort of p-adic cohomology theories that are sort of still being understood. And so hopefully there will be sort of more sort of interactions between these fields in the coming years. So yeah, so thank you very much. And I'll stop here.